Thank you. I'm going to talk about the IU's regions, hurricane forecasting, the global demand for fish, and the common thread that goes through this is the rise of the regional scale. That's been enabled by IU's. The example that I'm going to use is Maracus, the mid-Atlantic. It goes from Cape Hatteras, 1,000 kilometers, to Cape Cod. It's got that wide shelf. It's got a quarter of the U.S. populations. It's got major ports, critical habitats, offshore energy. It's truly an urbanized ecosystem, multi-use. Here's the way we sample this. We need spatial data. We get our own satellite data. We build our own products. Here's a coldest pixel, not warmest, coldest pixel to get the mixing. Here's rivers, plankton blooms. That's what's in the water. The next thing you need to know is where's that water going? So we build a HF radar network, 41 radars total, triple nested, multi-static, dual use. Dual use means we get ocean currents, we get the vessels that are in there, and we can set up in Oprah's backyard without disturbing her. That's a good network. Next thing is gliders. The gliders, they fly beneath the sea surface temperatures. They give us that 3D structure, multiple missions, many agencies, anything that can be put inside, on top, on the tail can fly on those vehicles below the surface of the ocean. We combine all that data in a data fusion center. This is our operations center. We fuse it into new products. We assimilate it into 3D models, and we use it for guidance, for our ships at sea, for our gliders in the water, and for the people on land. An example where we helped guide the people on land was Hurricane Irene. Irene forecast days in advance to track right through our network at the same scale, but the intensity totally overpredicted. A big gap in storm science. Why was that? Look at the global sea surface temperature used in those models. Warm days after the hurricane. Look at the coldest pixel. It cooled. 8 degrees C. That's a fire extinguisher on the hurricane. When was that applied? How do you know? You have to wait for the clouds to clear? No, the robots were out there. The robots were out there. They see exactly what had happened. As the eyes approach it, it happened in a few hours. That eye is going over cold water. When that eye goes over cold water, you can do 2 sensitivity forecasts. One over the warm water, one over the cold water. Look at the reduction in the winds. If you compare that to measured winds, what happens? Look at the RMS error go down. You have better ocean at the regional scale of the storm, you get a better forecast. But what about the fish? Those same surface temperatures. Let's look at the summer-winter SST difference, the largest in the world. 20 degrees, 24 degrees, migratory fish species. These fish care what the temperature is. If you know that, you can build models for the fish. Here's habitat models. This is what butterfish like. That range. If we look at that range with our models, we can see, did we sample the species correctly? Are we doing the assessment correct? Are we managing that fish species correctly? If not, can we add to that? We put gliders out there with fish sensors to check. Are they in the rivers? Are they hiding there? If we put sensors on those fish and have them talk to the gliders and talk to the people, do we get a better picture of what that temperature structure is? And if we have that, we can feed better back on the weather forecast, and we'll better understand our large marine ecosystems. That's important because there are 64 large marine ecosystems that produce 80% of the world's fish. That's the fish we need to eat. And if you look at the global population, 7 billion right now. Not everybody lives like us. 80 million without clean water, 1 billion without food, 1.4 billion without electricity. All in this same band. You'll see that band over and over again. If we look at what our kids are going to grow up into, 9 billion people, 2 billion more people added in the developing countries. On top of that, migration to the coast, to the megacities. Again, this is the place where the sea level's rising and the hurricanes are more intense. So they're going into harm's way. If we look at their needs, let's look at one need, water. Yeah, here's climate change. It's going to make a rough road, but you add the population growth and climate change, that's trouble. That's what they have to deal with in the next generation. So what do we need most? We need educated young people. This is 2 of my classes, one in Rutgers, one in the Canaries. What do I need to do to take these students to sea? How do we reduce the barriers to their participation and get them out there? One way is telepresence. The interactive in science and education enabled through the cyber telepresence of the Ocean Observing Initiative. Mike Crowley's going to talk about that. I'm going to talk about something else. I'm going to talk about omnipresence, the Global Glider Challenger mission. 16 gliders, 16 global class gliders flying around these ocean basins, all tweeting back their data to this to enable and create that next generation of of ocean explorers.
Good job.